So just a quick overview. So the first thing we're going to talk about is kind of where does a p-value come from? So again, not necessarily worrying about kind of equations or formulas, but really approaching it from a more big picture view and trying to kind of illustrate where that comes from through an example. And then we're going to talk about problems with the p-values, and then kind of directly related to that are going to be some alternatives to the p-value that can either be used in place of, or what I would kind of advocate more is in conjunction with a p-value. It's not necessarily replacing it, but trying to make sure we have kind of sufficient information to kind of be able to allow readers to have kind of an intelligent discussion around results. So where does a p-value come from? And we have this kind of magical p-value. And what we're really talking about when we think of p-values or hypothesis testing. I think when people think of statistics, you often kind of jump to this idea of p-value and significance, but it's really only tied into a specific component of statistics, and that's really hypothesis testing. And this is the one that's, I think, often used, particularly for any sort of trial. Often we kind of default to hypothesis testing, but I think it's important to understand what a p-value really is trying to do and kind of in what settings it is actually appropriate to use. So we're going to be talking about hypothesis testing, and this is how we're really going to build up what that p-value is. So hypothesis testing, just kind of what its goals are, is essentially, we hypothesize that we have some new treatment or some new exposure that we're trying to explore, and we think this treatment or exposure will affect outcomes in some way. So, if it's a treatment, we're hoping that it improves outcomes. If it's an exposure, maybe we're trying to either look at if it improves, or maybe we're also trying to understand if it potentially kind of worsens outcomes. So throughout this talk, I'm going to be talking a lot about coins because it's a really, I think, easy example to grasp and not necessarily tied into one specific research area, though with this group, it's a little more homogeneous in terms of kind of the research we're doing. So the example I'm going to use is there's a coin factory, and I think it's producing weighted coins. So my hypothesis is this new treatment, this coin factory, is producing weighted coins, those outcomes. I don't think it's a fair 50-50 chance of heads and tails. So what we really want to do when we're talking about hypothesis testing is we really want to try to convince a skeptic who thinks the treatment, does not work. Us as researchers often will think our treatment does work. Otherwise, why are we studying it? Why are we trying to kind of implement it? So, we think or we hope this treatment works, but what we really need to do is convince some skeptic who doesn't think it's going to work. And this skeptic essentially represents our null hypothesis. The null hypothesis basically being kind of the status quo, or that, there is no effect. In this case, the coin factory is not producing weighted coins, it's producing fair coins. That's kind of what a skeptic would assume from the start. There's no reason to believe from a skeptic's point of view that this factory is producing weighted coins. So our goal in hypothesis testing is to really convince the skeptic to reject this null hypothesis. We want them to conclude that the coin factory cannot be producing fair coins. I think this is a little backwards to kind of the way we maybe normally think about this, in that, we often think our goal should be to kind of prove the treatment works. But the way we're really trying to show a treatment works is by showing that it does not have no effect. So it's an interesting way of kind of framing statistics, in that we're not necessarily directly proving what we want, but we're trying to kind of disprove what we don't want. But that's kind of the way that the theory and the data collection stuff kind of works. This is kind of our best option. But again, it's kind of important to keep in mind that our end goal is to really reject that null hypothesis, and therefore we can conclude the treatment works. So to do this, we need data. If we're going to convince a skeptic, if I just go and try to convince them, hey, the coin factory is producing weighted coins and I don't provide any data, I'm probably not going to get very far. So we need to actually go ahead and get that data. And that's where kind of a classic study comes in. So in this study, we're going to enroll participants, which in this case are coins. So I'm going to enroll kind of 10 coins from the factory, and I'm going to record their outcomes. So in this case, I'm going to flip those 10 coins, and I'm going to observe how many of those were heads, how many of those were tails. So in this case, flip 7 heads. And then the question is, is this really enough evidence? Do I have enough data here? 7 heads out of 10 coins, is that enough evidence to convince the skeptic? And I think internally, we're all really good at this concept of, what is enough evidence before we're convinced something is no longer fair or something no longer works the way we think it is. I think internally, you're probably not going through and calculating p-values and calculating probabilities, but when you see 7 heads out of 10 coins, internally, you're probably thinking, is that reasonable? Could that happen just by chance? How rare is it to get 7 heads in 10 coin flips? I think we go about this, kind of everything we do throughout our day. We're kind of making these decisions on, is there something else going on in this situation? Or do I think this is kind of perfectly normal, just chance? However, in kind of research, it's not really enough for us to all have sort of these internal clocks on, what is considered unlikely, what is considered likely enough. So what we really want to do is really want to formalize this concept. And this is exactly what hypothesis testing and p-values are trying to do. We're really trying to formalize this process. I think a great example of kind of trying to represent this and trying to kind of make this more uniform is to think, how many heads would I have to flip in a row before you think the coin I'm flipping is not fair? If I flip 1 heads in a row, most people probably would not say that coin's unfair. If I flip 4 in a row, maybe there'd be a few people, but if I flip 100 in a row, I think the vast majority of people would say that's so unlikely to happen by chance, something else must be going on. But again, everybody's probably going to have a different cutoff. It could be 10, 15, 20, 100. And again, this hypothesis testing and p-values are really meant to kind of create a uniform kind of standard for how we should approach this, rather than everybody having that different kind of internal kind of clock on what's considered, too many heads in a row before it's considered a not fair coin. So what we really need to do in this process is to determine, what outcomes would we really expect if the null hypothesis is true. So in this case, if the coin is fair, what outcomes would we expect to occur? Is 7 heads out of 10 coins? How likely is that to occur? We know it's possible, but we really want to, get an idea of how likely these outcomes are to occur. This is exactly what we mean when we talk about the distribution under the null. So when we talk about the distribution under the null or the null distribution, we're really talking about what is the distribution of outcomes, a distribution of heads, in this case, number of heads, if that null hypothesis is true, if there is no treatment effect. So I just kind of talked about this briefly before, but it essentially provides the probability of all outcomes. So I can basically look at, okay, I observe this outcome. What's the probability that outcome occurs if the null hypothesis is true? And I could look at that for every single possible outcome in my data. Model assumptions will impact this distribution. So I'm not going to really delve into kind of the different types of model assumptions, but basically it's just important to know that, based on how you're measuring your outcome, what your null hypothesis is, do you have data that's correlated? Are you doing repeated measures, or is everybody kind of independent of each other? All these factors will influence what that null distribution may look like. We're not going to worry about that. What we do want to kind of focus on in our example is, how can we go about and actually determine the probability of every possible number of heads in 10 flips? Again, we're assuming the null hypothesis is true. So we're assuming we have a fair coin, and we're trying to go through and figure out, okay, what's the probability of 0 heads? What's the probability of 1, 2, 3, 4, all the way up through 10 heads? Now, this can be done in simulation. So I could just, literally flip up. If I had a coin that I knew was fair, I could literally just keep flipping that coin over and over and over and over again and figure out what those probabilities look like. You can do this kind of using computer programs as well for simulations. And that's really helpful if you have kind of complex data where it's really hard to pin down some of the assumptions. But in many cases, we have these nice theoretical distributions that have been determined that we can use directly. So there's actually an equation, and I'm not going to work out what that equation is. There's an equation that you can just plug in numbers, and you can actually determine that exact probability of 0 heads in 10 flips or 8 heads in 10 flips. And again, computer software can do this quite easily for you. So I went ahead and did that. So I kind of input, 0 through 10 number of heads, and I actually calculated the specific probability of achieving that many number of heads in 10 flips if that null hypothesis is true. So here we see the distribution under the null hypothesis. On the x-axis, we have the number of heads that we flipped in those 10 flips, and on the y-axis, we have the probability. So we can see, kind of in the 3 to 7 range, those are fairly high probabilities. They're all above 10%. But as we get closer to 0 or we get closer to 10, those probabilities get less and less likely to occur just due to chance. And again, the probability of 0 heads or 10 heads out of 10 flips is extremely unlikely. So what do we actually do with this? We calculated this null distribution, which tells us, what we think the data should look like if that null hypothesis is true. Essentially, how likely is an outcome to occur? But how do we actually use this null distribution with the data that we actually collected to be able to actually make some sort of conclusion on how unlikely our specific data is? Well, the first thing we can do is just look at, how likely is it that our data occurs? So, what's the probability of getting exactly 7 heads out of 10 flips? Well, again, we can just use this null distribution, and we can see when we look at the x-axis and we go over to the number of heads, we see 7 flips. We can kind of estimate that probability using this graph. I've calculated it directly using software, but you could, estimate this to be approximately, about 12% or between 10 and 12%. And in fact, it is about 11.5%, just under 12% if we calculated it. But that's generally not what we're interested in when we're thinking of kind of statistics with the null hypothesis. We're not necessarily interested in what's the probability of exactly something to occur. We're really looking at what's the probability of something occurring or something even more extreme occurring. So we're not talking about one specific event. We're talking about any event that is as or more extreme than what we observed. So again, if we're thinking of coin flips and we're expecting 5 heads out of 10, if that coin flip is fair, what's more extreme than 7? Well, it's 8, 9, or 10 heads. So that's really the range of values that we need to consider. We're not just looking at exactly 7, we're looking at 7 through 10. It's also important to note that I didn't do it in this example to kind of keep things a little more simple, but we often will also need to consider extreme results in the other direction. Again, that skeptic doesn't necessarily know if that treatment works or actually hurts people. As a scientist, we're hoping that treatment is helping people, but as a skeptic, that treatment could equally hurt somebody as well. So it's important to kind of consider extreme events in both directions. So it's not just 7, 8, 9, or 10 heads. We have to look at it in the opposite direction, which would be, I think, 3, 2, 1, or 0 heads, kind of the extremely low rather than extremely high. But again, just focusing on that upper half, we really see that the probability of 7, 8, 9, or 10 heads is about 17%. And that's just adding up the probabilities of 7 heads, probability of 8 heads, probability of 9 heads, and the probability of 10 heads. And this is exactly the p-value. So I didn't really give any kind of disclaimer at the head of time that this is what we're directly calculating, but kind of working through this example, we actually have reached the p-value, and hopefully we've gained a little bit of understanding on what that is. So basically the process that we've kind of gone through is we've created this null distribution, which is again the kind of the range of values and the probabilities of outcomes that we expect under the null hypothesis. And then we compared our actual observed data to that null distribution to try to calculate what that p-value is. And I think it's really important to note at this stage, we haven't made any conclusions about whether that coin is fair or not. The p-value itself does not kind of tell us directly whether we think that null hypothesis is true. Again, we don't know just based on the p-value whether that coin is fair or not. It's just a value, a tool that we can use moving forward to try to make some decision based on statistical significance. So that's kind of the next step is, how do we actually use this p-value to determine what is statistically significant and what isn't? So again, we talked about this kind of briefly at the start in a slightly different light, but conceptually, to determine statistical significance, it's the probability of getting data is so kind of unlikely under the null hypothesis that we'd much rather conclude something else. Again, if we think about the extreme case of me flipping 100 heads in a row, that's possible just due to chance. You can flip 100 heads all in a row with a fair coin. It's possible, but it's so unlikely that the vast majority of people would instead prefer to conclude that that coin is unfair. And that's just, again, that's exactly what we're trying to do with statistical significance. At what threshold do we have to cross before I say, I don't think this is due to chance anymore. I think there's something else going on, and I'd rather believe that there is a treatment effect than just assume, we got really, really lucky and hit the lottery with kind of this kind of sample of data that we got. So in this case, the probability of flipping 7 or more heads is about 17.2%. So, is this considered too rare to occur? At least for me, kind of just internally, about 20%, 1 in 5 chance of flipping 7 heads in a row, or not in a row, out of 10 flips. That doesn't seem that unlikely to me. That seems within kind of the range of what I could reasonably expect. I wouldn't be that surprised if somebody flipped 10 coins and got 7 heads. But, what about 10 heads again? What if they flipped 10 coins and all 10 of those were heads? Now we're talking about only about a 0.1% chance. That's definitely less likely, and I'm definitely more inclined to believe that that coin is weighted in favor of heads than kind of that previous coin that flipped 7 out of 10 heads. But again, it's not really enough to kind of just say, well, I think at this percentage this should occur, and somebody else can think of, well, I think at this percentage this is when we kind of cross that line. It's important to kind of have a standard unified kind of discussion about this. So some standard cutoffs were kind of used somewhat kind of just by chance. That basically started by a statistician was basically writing a kind of this paper on hypothesis testing and basically used as kind of 1 in 20 or 0.05 as kind of an example to use, and the statistical community just kind of took it and ran with it. So by far and away, if you were kind of looking at any literature, you'll see this standard cutoff of 0.05. Why? It's convenient having a standard, I think, for one. I just kind of talked about how it's it's challenging if every researcher is using a different standard. At some level, we need to have a standard starting point from which we can kind of discuss. And if you feel like you need to adjust that for your research, well, you know where that starting point is, and then you can provide some justification for why you think kind of your criteria should be different. So it's convenient having that kind of standard that we can all start from. But again, it's important to remember that that 0.05 is arbitrary. It also seems reasonable. So I don't really talk about type 1 error, but a type 1 error is essentially the probability of a false positive. And what this is basically, this 0.05 is basically doing is it's letting us know that we would expect, if the null hypothesis is true, about a 1 in 20 chance of a false positive. And again, there's no necessarily reason why that's kind of the gold standard or what it should be, but it seems to be at least reasonable that, okay, 1 out of 20 times we're going to get a false positive. We need to accept some false positive if we want to be able to detect anything. 1 in 20, again, seems reasonable. Is it the best we can do? I don't know, but it's certainly reasonable. But again, it's important to note, and I'm going to just kind of say this again, that 0.05 is arbitrary. So, all this kind of weight we put into significance it all comes down to this arbitrary standardized cutoff that was adopted and just kind of taken off in the research community without any kind of real reason to back it up other than it seems to make sense and it's nice to have a standard. So now we're going to talk about try to understand the p-value a little bit more. So this is going to be somewhat of a refresher on what we've just captured, but hopefully a little more explicitly stated to really refresh and ingrain some of these concepts for people who are less familiar with them. But the first thing to really remember is that p-value is calculated assuming the null hypothesis is true. So that's a very important assumption that we're making. We're assuming the null hypothesis is true when we actually calculate this value. So the p-value does not tell us what the probability is that the null hypothesis is true. Remember, we assumed the null hypothesis is true when we calculated the p-value, so we can't go back and use a p-value to try to say the null hypothesis isn't true in terms of probabilistic sense. We can't really keep going to this circle. We have to start somewhere and we have to end somewhere. And when we're talking about hypothesis testing and p-values, we start assuming the null hypothesis is true, and then we end up with the p-value. We can't then go in reverse and try to calculate what the probability of that null hypothesis is. So it's just really important to remember that we cannot interpret it as the probability the null hypothesis is true. It's important to note, again, that cutoff used for significance is arbitrary. It's helpful having that standard, but that cutoff is arbitrary. And the p-value is really a summary of two concepts. And I think this is important. It's a summary of effect size and it's a summary of precision. And both of these are important to research. Effect size basically tells us how large of a treatment effect do we think there is. Precision allows us to say how precisely can we measure that treatment effect. So both very important concepts, but unfortunately with the p-value, we're not actually able to separate these. So when we see a p-value that's either high or low, we don't know if that's driven by the effect size. We don't know if that's driven by the precision or if that's driven by a combination of both. So if you see a really, really small p-value, it could be still a really, really small effect size and just have really, really high precision. Similarly, if we have a really large p-value, it could be because we have a really, really large effect size, but we also have a very, very large precision to that estimate as well. And we can't separate those two concepts with the p-value alone. And misunderstanding these concepts can be very problematic. So I'm going to hopefully walk through, at least briefly, just a few limitations. So this certainly isn't an exhaustive list, but we have a few examples to illustrate what the idea is. And I think this t-shirt really sums it up pretty well. My p-value is smaller than your p-value. It really exemplifies the problem with just saying, we want the smallest p-value possible. That's not how we want to conduct research. That's not how we can determine what the best treatment effect is. We really need to be a little more intelligent in how we discuss results than just, oh, well, my p-value is smaller than yours, therefore my treatment is better than yours. So we're going to explore this through a few different examples that I just created. But it's important to note that the p-value, again, as I said, does not equate to effect size. I talked about the p-value being related to effect size and precision. So if we're able to hold things constant, precision constant, and only impact effect size, yes, a larger effect size will lead to a smaller p-value, again, if everything else is equal. But that's rarely the case in research. You change one thing in a study and everything in the data changes. So it's just really important to note that, yes, while a larger effect size can lead to a larger or a smaller p-value, it's really dependent on other assumptions that are generally not met. And that main assumption being that the precision is also often affected if we increase the effect size. If the effect size is larger, the precision can change as well. And there are other moving parts as well. So precision, that's going to help kind of drive what that p-value looks like. So we can't just say smaller p-value equals larger effect size, again, because it could be due to the precision as well. So here's a problem one, kind of an example that I have to illustrate. So, just based on these p-values of these two coin factories, which coin factory is less fair? So basically, I got 10 coins from each coin factory. I flipped, counted the number of heads, and I calculated the p-value. So in factory 1, I have a p-value of 0.018, and in factory 2, I have a p-value of 0.005. So just kind of internally, if people want to think about, based on these two p-values alone, if this is the only data I had to go off of, which of these coin factories would I think is producing coins that are less fair? And I think a lot of people would probably say, factory 2. And I think with the information we're given, that's a reasonable claim to make. Coin factory 2, it has a smaller p-value. This is the only data I have to go off of. I'm going to assume that that factory is producing less fair coins. But again, that doesn't necessarily tell the whole story. So what kind of one solution to avoid this idea of just trying to use p-values to determine if one treatment is more effective than the other? And the first is, and maybe this is just kind of intuitive, but I've seen issues with this in papers before where they don't report an effect size. But that's important to always report a measure of effect size. Say how much is this treatment kind of helping or hurting individuals compared to some other group? Don't just give kind of the p-values. This is often in addition to, not in place of a p-value. So they're getting at different concepts. The effect size is kind of the magnitude for which I think this will help somebody. The p-value is more a measure of probabilistically how likely or unlikely are these results to occur if there is no effect. So they're getting at different measures. So I think it's important to report both. So this isn't meant to say don't report the p-values and only report effect size, but it's really meant to say we should really be reporting both of those values. And this really allows us to just better understand kind of the clinical impact of an effect as well. So in addition to the clinical significance, it's often important to evaluate, is this effect big enough to actually be meaningful to patients? And if the answer is no, then it really doesn't matter what that significance level is. It's really important to kind of consider both the statistical as well as the clinical impact a treatment will have. So this is the same question as before, but now I presented additional information. So in factory 1, that was the factory that had the p-value of 0.018. I'm actually giving you the number of heads that I flipped. So I flipped 100 coins and 60 of them were heads. If I look at factory 2, 540 were heads out of 1,000 flips, and then kind of those corresponding p-values. So now the question is, which of these coin factories is less fair? And I think it depends how you measure it, right? We're probably more certain in that factory 2 is unfair, but factory 1 looks like it has the greater chance of being kind of a heavier weighted coin. So I think the question is still kind of unclear as to which of these coin factories would we actually conclude is more or less fair, depending on kind of how we're approaching the question of fair. Is it, which one is less likely to be fair, or which one has the greater kind of probability of being more extremely unfair? But with this addition of the effect size, we're at least able to have that conversation. We're able to say, okay, the p-value is a little larger for factory 1, but that effect size is also larger. Factory 2, we have a smaller effect size, but we also have a smaller p-value. Again, we can't necessarily, I would say, make a certain conclusion over which one of these is less fair just based on the numbers presented, but we now have a lot more information to at least have a discussion on. We can at least kind of more intelligently discuss what we're talking about when we're talking about, less fair. We have a larger effect size here, larger p-value. How should that be weighted? There's no kind of golden answer here, but this additional information really allows kind of the reader to kind of have an internal discussion over what they think they should kind of weight more importantly, smaller p-value or the larger effect size. The second problem, this will be the last problem I kind of talk about for p-values, is really using p-values to prove no effect. I think it's really tempting to see a large p-value and say, oh, we know that there is no effect. We know this treatment does not work. But we can't actually use a p-value to prove there is no difference. So it's just not actually mathematically possible. And it's important to note here that the absence of evidence is not evidence of absence. And I'm hoping to illustrate that kind of through an example moving ahead here. So the first case we look at is, what if I flip 2 coins and get 2 heads? What's the probability of 2 or more heads if that coin is fair, well, it's about 25% chance. So I have a 25% chance of getting a 2 heads in a row if I flip 2 fair coins. So based on that, I would fail to reject the null hypothesis. 0.25 is greater than that 0.05 that we typically use, so we're not able to reject that null hypothesis. But based on those 2 flips, how many people would be willing to bet that that coin is perfectly fair? And I would say, hopefully not many people. There's no evidence to believe it's not fair, or at least not sufficient evidence to believe it's not fair, at least in my view. But we would also, say if this coin had heads on both sides, we'd also flip, 2 heads in 2 flips. So I think it's important to note that, there's really no indication that this coin is fair just by flipping, 2 heads out of 2 flips. If anything, we're slowly approaching this idea that the coin is not fair. We just need, a lot more flips to kind of prove that, even though that p-value is kind of larger than that cutoff we would use. So as I said, we really need more, data. So here, suppose I flip 1,000,000 coins. So we're kind of really upping the game here. And I got, 500,001 heads versus 499,999 tails. A p-value of 0.992. So now the question is, well, how many people would be willing to say this is a fair coin? And I think a lot more people would be willing to say, yeah, I think that coin is fair. There's a lot of data, 500,001 versus 499,909. Those values are pretty close. And the p-value is 0.992. Kind of to which that, are these coins fair? Again, I think more people would say yes here. But to kind of counter that and be maybe a little facetious, I would say, suppose the chance of heads is actually 50.00001% chance. So, we would need trillions of flips to be able to detect a difference this small. But in a very kind of literal sense, this null hypothesis is still incorrect, right? 50.00001% chance is not 50%. It is not, they are not exactly the same. This null hypothesis is 100% false in this case. So, while conceptually we might view these coins as fair, in a rigorous statistical setting, this is not the same as the null hypothesis being true. And in which case, my kind of follow-up question would be, is this really a helpful way to approach a research question? If I can't say a coin is fair, even though it's 50.0000001% chance, is that really helpful? I'll say, probably not. So this is really just meant to illustrate that p-value is really not helpful in trying to prove no effect. Again, it's extremely difficult. You essentially need an infinite amount of data to be able to prove that, because you can have such an arbitrarily small difference from the null hypothesis, and that null hypothesis is still wrong, but clinically, there's absolutely no kind of meaningful difference. So I think a better question to ask, particularly if we're talking about kind of this idea of no effect, is, is the coin weighted in a meaningful way? So can we rule out that there is a meaningful difference? I just kind of showed on the previous slide that, it's basically impossible to rule out that there is no difference from the null hypothesis. The null hypothesis is true. But what we can do is try to make a conclusion about, is there a meaningful difference? And we can potentially conclude that there is no meaningful difference. So we're not truly accepting the null hypothesis, but we're basically saying we're close enough to the null hypothesis that I don't think this treatment is worth pursuing anymore. Again, this is ultimately a clinical question for kind of how far away do you have to be before it's clinically relevant. But we can use statistics to help better address that idea and kind of assist in that clinical decision. And to do this, I'm going to introduce the idea of confidence intervals, which basically allows us to say, based on our data, what effect would we actually expect? So rather than thinking of it, hypothesis testing as this kind of just probability of trying to say, is the null hypothesis, something we should believe or not, we can say, okay, well, based on our data, what do we actually expect the actual effect to be, and kind of focus on what effect we think it is, rather than a direct comparison between that effect and our null hypothesis. That's this idea of confidence intervals. So if you're not familiar with confidence intervals, a very kind of quick overview is essentially it's a range of values that we can create from our data that gives us a range where we think the true effect lies. So in our sample, we collect data, we measure an effect. We don't know if that effect represents the true population or not, because we just have a sample of our population. So we create this confidence interval, which basically gives us a range based on our estimate from where we think that true value should be. Like the p-value, it contains information on effect size and precision, but it's a lot easier to kind of separate what's due to precision and what's due to the effect size. You can actually use it to replace the p-value to determine significance. So you can't actually calculate a p-value. You can't get that probability. But if you're going to use this flat out, are you significant or not? Are you above or below your 0.05 cutoff? You can use a confidence interval for that as well. But again, we are losing information. We don't have that p-value. We don't have that measure of probability. So I wouldn't necessarily view this as just to kind of replace and move on. This is still something you'd often replace kind of in tangent. So you often have a p-value, effect size, and confidence interval in the perfect world. Publishing space is limited. We can't always report everything, but as a statistician, kind of reporting everything is usually the way to go. So solution 2, so we can't use a p-value to prove this is no difference. There's no difference. So if you can't use the p-value, how do we solve that? So just kind of rehash from before, but now we can really introduce this confidence interval to get an idea of, is there kind of a meaningful difference, or is there the potential for a meaningful difference from our null hypothesis, or can we conclude that there is no meaningful difference? So if we look at the same example, flipping 2 or more heads, if the coin is fair, again, we said that p-value is about 25%. If we create a confidence interval around that, the confidence interval would actually range from 19.8% to 100% chance of heads. So this is a very wide range. And I say from this range, we can kind of conclude that we really just don't have enough precision. This is such a wide range, it's really hard to make any sort of conclusion at all whatsoever. So this is the case where I'd say, well, we really can't make any conclusion on whether this coin is fair enough or not, but this is because we don't have sufficient data. We don't have enough precision. This interval is way too wide. We're not able to make any sort of intelligent conclusion from that. So kind of the conclusion is still the same as the p-value in this case, but in the second example I gave, where we flipped 1,000,000 coins, we'll reach a slightly different conclusion. So again, if I flipped, 1,000,000 coins, I got 500,001 heads, 499,999 tails. I got my p-value is really large. But when I create the confidence interval ranges from 49.9% to 50.1%. Again, I don't know that the null hypothesis is true. It could be the true effect could be 49.9, or it could be 50.1. But if I say, well, to really matter if this coin is weighted, it needs to be at least, maybe 55% chance of heads. Anything less than 55% chance of heads and the patient doesn't care. I don't care about that. I can conclude from this confidence interval, because I'm confident that the true probability should range from 49.9 to 50.1, I can safely conclude that there is no meaningful difference from 50%. There still could be a difference, but I'm very, very confident that that difference is not going to exceed 50.1%. And again, is 50.1% kind of clinically meaningful or not? That's that kind of clinical decision you have to make. In some cases, that extra 0.1% might actually be really meaningful, and we're not able to make a conclusion here. But in other cases, like I said, if we need a 5% increase, we could conclude that this 50.1% is not clinically meaningful, and these coins, for all practical purposes, are fair, even if they're not, actually literally a fair coin. So again, I can't conclude the coin is fair, but I would expect this difference is not meaningful, assuming 0.1% difference doesn't matter in this setting. So just a quick kind of summary. So kind of p-values are generally not enough. It's really hard to make decisions based only on p-values. So at the very minimum, we should always include an effect size. So we have other measures. We should always incorporate an effect size. Measures of precision can be particularly helpful. So this could be things like even just including your effect size in your standard error or a confidence interval. And I guess the question, should p-values be used at all? I kind of talked about how kind of some of the pitfalls they can fall into and how confidence intervals can be used in place of some aspects. And so let's explore some examples first. We're not getting to those examples here, so that line should be gone. But essentially, should they be used at all? I think the answer is yes, they should still be used, but I think they really need to be kind of balanced with other information. And I think we need to make sure we're going into kind of literature with a good understanding of what that p-value is truly representing, and make sure we're not kind of misunderstanding or kind of over-interpreting what that p-value reflects. So there's some very kind of quick guidelines. Tend to never only present significance. Always have some sort of value of what that p-value actually is, for one. So don't just report yes significance, no significance. Report what that actual p-value is, but also again an effect size, confidence intervals as well, to help kind of round out information that the p-value doesn't capture. All those values capture a slightly different piece of information. So let's kind of give it all and then kind of let the reader kind of interpret that information as they will and kind of weight it how they want to. I think it's important to place less emphasis on significant results in general. Other statistical and clinical aspects are just as important. Again, that significance cutoff is arbitrary. And I think there's this kind of the pressure to have significant findings, but it's also really important to understand if treatments aren't that effective, if results aren't, significant. It's important to understand that as well. And I think this is just a problem with the larger kind of research environment as a whole, though I think we're slowly getting into kind of a better environment where, research is important kind of regardless of what those results are. And we don't need a significant finding for the research to be kind of important or valid. And it's always important to interpret the clinical impact of the effect as well. So hopefully kind of illustrate that at least briefly with some of the examples, even if I didn't, target it directly, but it's always important to remember that, the whole idea of research is to really have an impact on a patient. It's not just to prove, hey, my treatment is effective, like, look at that, I'm great, I'm so smart. It's really to, well, can we translate that to kind of a meaningful impact on patients? So it's important to, even when you have a statistically significant result, to really critically think and say, but is this effect really large enough such that my patient is going to, want to go through this treatment or not? And then again, guideline includes some estimate of precision. 99% confidence interval is fantastic if there's a space for it, but there are kind of other alternatives such as standard errors, or even again, just at the very minimum, including an effect size as well to give some framework for that clinical relevance in addition to the significance. I'm happy to take any questions if there are any.